Welcome, ladies and gentlemen, to this video tutorial. Let's take a look at exercise 3.4, number 4 on page 176. And what this question says is we have some function on an interval from a to infinity, so that f of x is greater than 0 for all x in the domain of the function. And now what do we have to prove? We have to prove that the limit as x tends to infinity of f of x is equal to 0 if and only if the limit as x tends to infinity of f of x 1 over f of x is equal to plus infinity. Okay, so notice these words, if and only if. So we have to do two proofs. We have to assume this statement and prove that one, and then conversely we have to assume this statement and prove that one. So let's call this 1 and let's call that 2. And as always, we cannot do these problems if we do not know the definition. So let us prove 1 implies 2. So we will assume 1. That is the limit as x tends to infinity of f of x is equal to 0. That is 1. Remember, we are assuming this, so this is a shop. We can buy things from this shop, but we need to know what the shop is selling. So let us write out the definition of what this means. This means for every epsilon greater than 0, there exists an m greater than 0, so that for all x in the domain of the function, if x is bigger than m, then f of x minus 0 is less than epsilon. And this is a shop. If we bring an epsilon, this shop will sell us an m that works with the epsilon that we bring, but we have to bring one. Okay, and now let us write out what we have to prove. Well, we want to prove that the limit as x tends to infinity of 1 over f of x is equal to plus infinity. Let's write out what that means. That means for every big E, there exists a big M, so that for all x in the domain of the function from a to infinity, if x is bigger than m, then 1 over f of x is bigger than e. So that is the statement that we have to prove. Okay, so let us first write out our proof outline. So here we will now prove we will write our proof of the statement that we have to prove. So let us take any big E. So what we're doing is we're going down the statement that we have to prove, and we are structuring our proof. So we take any E. And then we have to show that there exists an m. So we have to define an m. And this m needs to be positive. We don't know how to do that at the moment. Then we have to show for any x in the interval from a to infinity. So take any x in the domain of the function and assume that this x is bigger than m. And now what do we want to show? We want to show that 1 over f of x, we want to show that that is bigger than big E. So that is what where we want to get. So let us write it this way. Consider 1 over f of x, and that we want to get bigger than E. Okay, so here we now have our proof outline. Okay, so now somehow we need to use our assumption. And what we will do is, well, this E tends to be, well, the intention is for this E to be big. So this is a big positive number. If we take 1 over E, then 1 over E is going to be small. So let us try that and see where we get. So let us use, using, and let us call this assumption A. So we're going to use 1 over E. So E is not 0, so dividing by E is not a problem. So using 1 over E in assumption A, so 4 epsilon in assumption A. What do we get? We get that there exists an m, but just to, so this m and that m is not the same. So we're paying with 1 over E and we're getting some positive number out. So what I'm going to do is I'm just going to call it something else, put a different sticker on it. So there exists a k, so that if x is greater than k, then absolute value of f of x minus 0 is less than 1 over E. Because we paid with 1 over E, we paid with 1 over E, so the number that we get out works with the 1 over E. And also, notice here, remember in the problem statement, f of x is positive. So minus 0 doesn't change anything, and f of x is positive, so we can get rid of the absolute values. And this, I think, will get us there. So what we will do is we will define our m, take our m as k. So then if we assume that x is bigger than m, we defined our m to be k. So then x is also bigger than k. And then we know that f of x is less than 1 over E. And if f of x is less than 1 over E, then 1 over f of x is going to be, so if we think about it, e goes there, 1 over f of x is going to be greater than e. And that finishes the proof. And let's write it this way, then, or therefore, 1 over f of x is greater than e. So this finishes the proof of 1 implies 2. So we have now proven 1 implies 2. Now we still need to prove 2 implies 1. And the proof is very similar. So I will go a little bit faster. So proof 2 implies 1. And now I'm going to not write out the definitions. I'm going to go straight into the proof. However, what I want you to do is pause the video now, write down the assumptions, and write down the statement that we have to prove. And compare how we use our assumption and how we structure our proof. So when you're starting out, it's always a good idea to write out the definition of your assumptions and the exact statement that you have to prove. So we want to prove that f of x, that the limit of f of x is equal to 1 as x tends to infinity. So using the definition for every epsilon, so let or take any epsilon greater than 0, then we have to define an m. Definition says there exists an m, so that for any x in the domain of the function, so take x in the domain of the function, if that x is bigger than m, so assume x is bigger than m, and where do we want to get now? We want to show that f of x minus 0, we want to get to less than epsilon. So we will assume 2, and remember epsilon we should think of it as a small positive number. So 1 over epsilon is a large positive number. So we will use 1 over epsilon for e in our assumption 2. So using 1 over epsilon for e in our assumption 2, what we get back some positive number. I'm going to call it k. There exists a k greater than 0, so that if x is bigger than k, then 1 over f of x is bigger than 1 over epsilon. So we will define our m as k, and we assume that x is bigger than m, so x is bigger than k. But if x is bigger than k, then we know that, oops, I'm jumping the gun here, then we know 1 over f of x is greater than 1 over epsilon. So from here everything is positive, so multiplying everything doesn't change the direction of the inequality. Everything is positive. Our assumption said that f of x is positive everywhere. So absolute value of f of x minus 0 is equal to f of x, but that is less than epsilon. And that finishes the proof. Okay. So here we have now shown that the limit as x tends to infinity of f of x, if that is equal to 0 and the function is positive, then 1 over f of x, the limit as x tends to infinity is equal to plus infinity. So we can think of what happens. So f of x remains positive, so but becomes smaller and smaller, tends to 0, and then or 1 over f of x tends to infinity. And you can think of the function that sends 1 to 1 over x. So the limit as x tends to infinity of 1 over x, that is definitely an example of a function that for which that limit is equal to 0. So on the other hand, 1 over x, that tends to plus infinity. So this function is an example of a function that satisfies these conditions. Okay. So that is it for this video tutorial. I will see you in the next one.